Lesson 6, modeling with linear functions. So we definitely use linear functions quite a bit to model real-world problems. These are definitely going to be more interesting, I think, because they have application. So let's keep our brain straight about the facts for our linear models. So all our linear models come in the form of y equals mx plus b, where our parameters are the slope or the average rate of change and our y-intercept where we begin. So slope m tells us how fast the output is changing relative to the input. So therefore, that's our change in our y over our change in our x. Okay, the delta y over the delta x. Then it says the y-intercept tells us how much we start with, or the output starting value at x equals 0. So this first exercise, I'm going to have you guys do on your own and come to class with it. It walks you through pretty nicely to get through that problem. So come to class with that one done. We are going to take a look at question 2 on our together. So it says, sometimes the information we have about the linear relationship does not include the starting value, okay, that y-intercept. Let's take a look at that type of situation. So Kirk is driving along a road at a constant speed, okay, that's pretty important. He's driving directly towards Denver, so he's at some location and he's going to Denver. He knows that after 2 hours of driving, he is 272 miles from Denver. That's not how far he's traveled. That's how far he is from his ending point. After 3.5 hours, he is 176 miles from Denver. So summarize the information given in the problem as ordered pairs, where the number of hours h is the input and the distance d is the output. So we are talking about 2 hours, 272 miles from Denver, and after 3.5 hours is 176 miles from Denver. Hours and distance, okay? Hours and distance from Denver. Part B says, calculate the change in the d over the change in the h. So the change in the distance. So are we, as we're traveling, are we getting closer to Denver or further away from Denver? And then think about when we're dealing with our hours, okay? Are the hours increasing or decreasing as time goes on? So it set this up in our function notation. So what is the distance at 3.5 hours? And the distance at 3.5 hours is 176 minus the distance at 2 hours, which is 272, divided by the change in the hours. And when we do that subtraction, we end up with negative 96 over 1.5. So let's make sense of that. So that's negative 64 miles per hour. Now that sounds kind of weird because our rate is miles per hour, but it's negative. So let's see what question C says. I bet that's going to address why that's negative. It says you should have found that the rate of change, that rate of change that we just calculated, was negative. Why is it? Explain what is physically happening to result in this negative rate of change. So think about what's happening. Okay, and if I think about this sort of graphically, at time 0, if we start, and remember, it's the distance from Denver. Okay, at time 0, he could be way up here. Distance, okay, that's my distance, and that's my hour. So at time 0, he's this far away from Denver. At some point down here, as time has gone on, he has gotten closer to Denver, so therefore we've got that negative slope. Okay, therefore that's why it's that negative rate of change. So Kirk's distance is decreasing. Okay, distance is decreasing as time is increasing. Assume the relationship is linear, which it would be because we're talking about a constant speed here. Write an equation for the distance d as a linear function of the number of hours h. So we know that our average rate of change is negative 64 times h, and then plus some b, right? We don't know how far he is from his house. We haven't found that out yet, so we've got to do some work here to get to that point. So I'm going to choose to use, I don't know, I'm going to choose to use this second point here on the 3.5, 176. So my 176 is my d, equals negative 64 times the h that goes with that 176, which is 3.5, plus b. Taking that, and we end up with b is equal to 400. Well, what is that? 400 miles. What does that mean? 400 miles is how far Kirk lives from... Uh-oh, my stylus is acting wacky. I'm going to pause. Okay, I'm back. Phew, getting a little nervous there. So now we can write our equation. So, uh-oh. I'm not doing that. The stylus that I write with clearly has a mind of its own today. So let's see if I can get it to not do that. I'm going to pause again. All right, I'm back. We're going to try this one more time. Let's see what happens with the stylus when I go to write. Okay. Oh my gracious. Here we go. Okay. Let's see if I can get through this. D is equal to negative 64h plus that 400. I'm going to pause again and just go and do this on the smartboard. Okay, guys, I'm back. I'm on the smartboard now. So it says, how far did Kirk start from Denver? So we talked about that. We just found that that 400 is our y-intercept. So he's 400 miles from Denver. Right? Show the work that leads to your answer. So what do you mean by that? Well, if we use our equation and we think about it, how far is he from Denver? My time would be 0 because I haven't left the house yet. So if we think about that, at d of 0 is equal to negative 64 times h plus 400, okay? That would definitely be able to verify our work. After how many hours will Kirk arrive in Denver? Okay, so we're looking for our time here. Show the work that leads to your answer. So we're going to, again, rely on our equation. We're looking for the h, so then what would the d be when we're in Denver? So we have arrived, so how far have we traveled? So we've traveled that 400 miles. So how far we're in Denver? So we're at 0 miles. We've gotten there. Negative 64h plus 400, and we end up solving for h, and we get 6.25 hours it took him to get to Denver. You guys are going to do question 3. So let's go ahead and hop over to lesson 7. So more modeling. So this is more of the same thing. And we are going to do question 2. You do not have to do question 1 on here. We are going to do question 2 together. It says the cost C in dollars of running a particular factory that produces W widgets can be modeled using the linear function. So they're giving us our function. So the cost of W, C of W is equal to 1.25. There's our rate of change. And there is our starting. So it says, how do we interpret the fact that C of 100 equals 2,300? So what does that mean? Okay, the 100, that's our W. That's how many widgets? Okay, 100 widgets. So then what is that $2,300 represent? That costs $2,300. Okay, that's how much the cost is, $2,300 to produce 100 widgets. Okay, $2,300. So now it says, part B, give a physical interpretation for the two parameters in this equation. So in other words, what does that average rate of change mean? And what does that y-intercept, meaning what is the slope and what is the y-intercept? So the 1.25 is our unit cost to produce, to make one widget. So then what does that 2,175 represent, meaning our y-intercept? Okay. So that says if no widgets are produced, meaning our W is 0, okay, the factory is still putting out $2,175 to operate. Okay, so it's the factory's cost to even be running, to be open, to have people in there working. So they're not producing any product, 0 product, but it's still costing them $2,175 a day to even sort of open the doors to function. All right, go ahead and flip it. You guys are going to do question 3 on your own and come to class with that. Then question 4 is going to be our warm-up in class. Okay, so we'll do this as a class when you come to class. All right, so warm-up, that one you're going to do on your own, and this one looks shockingly like the one I did in the previous lesson, so you can use that to go back. All right, we'll see you in class.